Hi all, welcome back to my channel. In the previous videos, we learned about what is time complexity and its different types. Today's video is very important because we will actually calculate the time complexity of code. By the end of this video, you will be able to look at any code and instantly guess its time complexity. So the rule here is very simple. Count how many times the main statement runs as input grows. So let's apply this rule step by step. So the first example here we have is a simple for loop where we have a single statement. So since this is just a print statement, we can consider this as is a constant time, so big of 1. So only thing is now we have to calculate the time complexity for this for loop. That means how many times this for loop runs for the input size n. So if the input size is 5, let's say, then this system.out.println will get executed for iteration 0, 1, 2, 3 and 4. That means 5 times, which is equal to the input size n. That means it is growing linearly. So this is how we say the time complexity for this is big of n. So the rule of thumb is, irrespective of the constraint, first come with a small input size like 3 or 4 or 5 and then calculate how many times the for loop or function is getting executed. Let's move on to the second one. Here we have two for loops, so that is nothing but nested for loops, and again a simple statement, that is print statement, which takes the constant time, so big of 1. So now we have to see this how these two for loops and how many times this have been iterated. So again let's take a small input size as 3 and for I and j. So for input size 3, the outer for loop will go for up to 3, that means 0, 1, 2. So when I equal to 0, then j's will start from I and it is going up to n. That means 0, 1 and 2, right? And when I increments, again j will start from I, that means 1 and 2. And then again I increments to 2, then it will start from 2 and it becomes 3 and the condition fails and it comes out of the inner for loop, and here again I increments to 3 less than 3, the condition fails and it also comes out of the outer for loop. So if you see now how many times this have been executed, that is nothing but 3 plus 2 plus 1, this is 6 times. So to derive the time complexity from this, if you see this is 3, nothing but our input size itself, so that means n, and this is nothing but input size minus 1, n minus 1, 3 minus 1, 2, and this one is n minus 2. So basically we are going up to we get 1, that means n plus n minus 1 plus n minus 2 plus so on until we get 1. So this is nothing but sum of n numbers, and we have formula n into n plus 1 by 2. This is nothing but n square plus n by 2. So for finding the time complexity, we have to consider only the highest degree. So the time complexity for this algorithm is big of n square. So just by looking also we can say very easily that this outer for loop will run for n times, and this inner for loop, even though it is decreasing gradually for each iteration of I, but at max it is actually running for input size n. If you see here, when I equal to 0, j also went up to input size n, that is 0, 1, 2, that is 3 iterations. So we can also say this also at max runs for n times. So n into n, it is n square, and this is the time complexity big of n square. So now we have the third example. Here again we have two for loops. So by seeing instantly we might guess right like this, the time complexity is big of n square like the previous one, but not. Let's take a simple example, like again n equal to 5 as our input size. So when I and j, so when I starts from 1 and it's going up to n, that means 1, 2, 3, 4, 5. And if you see the inner for loop j, it is starting from 1 and independent of I, and it is incrementing by multiplied by 2 each and every time. So 1 and again 1 into 2 is 2 less than equal to 5, 2 into 2 is 4 less than equal to 5, and 4 into 2 is 8, 8 less than or equal to 5, the condition fails. So this 1, 2, 4 is executed for each iteration of I. This is a j value. So even though the outer for loop executed for n times, the inner for loop, if you see, it's multiplied by 2 and it's executed only for 3 times for each iteration of I, and it's immediately getting stopped, or the condition is failed, when j multiplied by 2 is greater than n. So if you see this 1, 2, 4 more closely, this is nothing but 2 power 0, 2 power 1, and this is 2 power 2. And the next one is 2 power 3, this is nothing but 8, which is not executed because 2 power 3, 8 is greater than the input size 5. So now here we can say like this: 2 power k less than or equal to n, the j for loop is executed for each and every time when this condition has been satisfied. So to find k now, when it goes that side, it becomes log to the base 2 n. So on an average we can say as k equal to log n to the base 2. So this is the time complexity for this inner for loop. So together we can say as outer for loop takes n times and inner for loop takes log n to the base 2. So nothing but we can just simply say the time complexity is n log n. So only rule of thumb is here, whenever this loop or function is multiplied by 2 or divided by 2, the time complexity would take is log n to the base 2. So again, simple approach, this takes n, this takes log n, that is nothing but n log n is a time complexity. Moving on to the fourth example, now here we have functions. So here the function is calling the same function, nothing but a recursion. So function calling itself. But here if you see, the parameter which takes the integer n, it's getting decreased each and every time. And here we have the base condition, when n equals to 0, we are returning out of that function. So let's take a simple one, n equals to 3. As you all know, for the recursion we always follow a stack. So first we will call function 3. Since it's not equal to 0, we'll go for this statement n minus 1. So function 3 minus 1 is 2, f of 2 is called, and then again it's not equal to 0, then f of 2 minus 1, f of 1 is being called, and then here f of 1 again not equal to 0, but here this will call f of 0. So when f of 0 is called, immediately it returns because it satisfies this base condition n equals to 0, and we come back to f of 1. Since there are no other statement in this example after calling this function, so it executes, or it comes to the closing brace and then it comes out of the function, and similarly it's for f of 2 and similarly it's for f of 3. So on an average we can see here these functions have been called for 3 times, which is equal to our input size, so it is growing linearly. So this is how we say the time complexity is big of n. Let's move on to the fifth example. Here we have a function which takes the integer parameter n, and the base condition here we have is n less than or equal to 1, it returns, or it returns from the function call, and then again the function is calling the function itself, but here the input size is becoming half. So as we have learnt already before, when the input size is becoming half or multiplied by 2, the time complexity is log n. So let's just understand by taking a simple example. When n equals to 5, so that means for a recursion we know that it takes a stack space. So for f of 5, it starts, and since the base condition less than or equal to 1, 5 less than or equal to 1 fails, so f of 5 by 2, that is f of 2 is called. Again f of 2, 2 less than or equal to 1, base condition fails, then f of 2 by 2, f of 1 is called, and when f of 1 executes, you saw that it satisfies a base condition, so it immediately returns, and we don't have any other statement after the function call of input size when it became halved, so it directly comes out of the function. See, at max we have 3 calls here, that is f of 1, f of 2 and f of 5. So immediately when we are reaching 1, we are returning from the function. So that means when n by 2 power k less than or equal to 1, we are still in the function itself. That means the stack is growing. So to find k value, it's nothing but 2 power k and k equals to log n to the base 2, which we saw earlier. So here how we got the time complexity as log n. So only remember that any loop where the variable multiplies or divides by a constant, then it runs for big of log n. This is a core DSA insight. So once you get this, many problems becomes easier. Let's move on to the sixth example, which is the last one. Here we have a function again which takes the integer parameter and the base condition, that is when n less than or equal to 1 it returns, and here we have two n by 2's function. So we can't say like this takes big of log n and this takes big of log n, so altogether we can say it is as log n as the time complexity. It's not like that. Since this is a recursion which two function calls have been made, we have to see this in terms of a tree. So let's take a small example now. Let's take n equals to 5. So when n equals to 5, first it checks the base condition, it fails, so it goes for f of 5 by 2, that is 2. Then if you see, this is executed now, this is still yet to be executed. So now f of 2, again 2 less than or equal to 1, base case fails, so again f of 2 by 2, it's 1, and again f of another 1, okay, because we have two function calls here, is yet to be executed. So when f of 1 is executed, it satisfies the base condition, it returns to f of 2, and now the other function of f of 2 is called, that is f of 1, and it also returns. And then this f of n by 2 function call has been completed for f of 5. That means the first function n by 2 is completed. So it goes for the next function call for n by 2, that is f of 2. If you see, this is same as the left subtree. So similarly we have f of 1 here and f of 1. So basically the total number of function calls here is 1 plus 2 plus 4, that is 7. So the function calls depends here the height of the tree. So what is the height of the tree is the number of edges, or at max we have is 2. So height of the tree is 2. So how the height of the tree is calculated is, if you see, we are stopped until we reached f of 1 here, right? So that means when n by 2 power k is less than or equal to 1, the tree is growing. Became 1, we are stopped, that means it converted to a leaf node. So here we can say the k is again log n, as we have seen earlier. So that means the height of the tree or the complexity is log n. Now for f of 5 we have 7 nodes. So for f of 10 or whatever the input size is, it would be like this, right? The pattern would be 1 plus 2 plus 4 plus so on and 2 power h, right? This is how this we can consider as 2 power 0 plus 2 power 1 plus 2 power 2, and 2 is the height of the tree here. So this is nothing but a geometric progression. So for the geometric progression we have formula as r power h plus 1 minus 1 by r minus 1. So here r is 2, that is the common ratio. 2 power h plus 1 minus 1 by 2 minus 1, it is 2 power h plus 1 minus 1, and substitute that h equals to log n. 2 log n plus 1 minus 1, that is 2 power a plus b is nothing but 2 power a into 2 power b. 2 power log n, that is base 2 is n into 2 minus 1, this is 2n minus 1. So the time complexity we should always consider the highest degree, so it is big O of 1. See how it is changed from log n to n, right? So it's how we calculate the time complexity for the recursions having more than 2 or 3 the same function calls. We might find some difficulty in finding the time complexities for this recursions, so that is why we use powerful shortcut called master theorem, and that's exactly what we'll cover in the next video. I hope this video helped you to calculate the time complexity and practice these examples, because once this clicks, coding interviews becomes much easier. So thank you once again. See you in the next video.